Hello class, I know you have missed me just tremendously. Organic chemistry, I know you've been out there just pining away for some organic chemistry lectures. So here I'm finally back, lecturing to a video camera, which is exceedingly strange for me. Anyway, we're gonna move on. And so today I'm covering parts of chapter 11, right? Just for your knowledge, we'll probably only cover chapters 11 and 12, and then that'll probably be it. But anyhow, chapter 11, free radicals. That means one electron all by itself, not a pair of electrons. So let's take a look here. Free radicals can form when bonds break homolytically. Break homolytically. Simply meaning that the bond breaks in two, each atom getting one electron. So something like this, just generic XY. We have homolytic cleavage. Again, for a single electron, you use a half arrow. Like thus, right? Creating two free radicals, right? So there you go, homolytic cleavage, right? Again, half arrow. Let's take a look at what this actually looks like in the orbital, right? This is going to be kind of a pain in the butt because I don't have a lot of board space, as you can see, so I'm going to be doing lots of erasing. Remember, when we had a carbocation, we had sp2 hybridization, okay? And there were no electrons in an unhybridized p orbital. When we had a carb anion, which we really haven't talked about hardly at all, we actually have sp3 hybridization with two electrons in it. But let me just draw this out, right? So again, here we go, carbocation. We're gonna have da-da-da-da. Something like that, and then again, carbocation, right, this has a plus charge. We simply have an empty p orbital. Okay, that's what we have, right? I guess I'll put a plus here, right? There's no electrons in there, okay? Let's take a look when we have a carb anion. We drew this a long time ago in the first part. Let's take a look at carb cation, anion. Right? What does that mean? A minus charge, right? Here we have sp3. So let me write this down here. sp2, right? The rest of these are sp2. This is an unhybridized p orbital, okay? Here we're going to have sp3 hybridization. Remember with an sp3 hybrid, the lobe on the one side was smaller, okay? So this is sp3, all right? And both of our anions are in there, or both of our electrons are in there, right? Again, empty p orbital, hybridized sp3, right? If we take a look now at a free radical, we can look at it as either way, as either sp2 or sp3. Again, this is really kind of a pain in the ass, sorry, having a constant erase here. Okay, so again, you can look at it as if it was sp2. This is sp2. This is a p orbital, unhybridized p orbital, right? The rest of these are sp2, unhybridized p orbital. Again, the lobes on both sides are the same. Or we could have this, we could have an sp3. Think of it as an sp3 orbital. Okay, either or. This will be important later on for looking at the chemical reactions of what's going on. All right? Now let's look at the stability of free radicals. Of carbon free radicals, that is, I should say. Okay, formal radicals do not have a formal charge, right? But they are unstable because they don't have a full octet. Remember the octet rule? Groups that can push donate electrons toward the free radical help stabilize it, okay? So we're going to have increasing stability here. And this is actually similar to a carbocation, okay? We're going to see that a methyl is the most unstable, primary, secondary, tertiary, getting more stable, which you should also remember from the mass spec section that we covered, okay? So we have our methyl free radical. Right, the carbon atoms here, this is the methyl, okay? This is the most unstable. Then we're going to have primary. Connected to one other carbon, right? Then we're going to have secondary. Connected to two other carbons, and then what finally, we're going to have tertiary. So again, methyl, primary, connected to one other carbon, right? Secondary, connected to two other carbon atoms. And then we have tertiary, connected to three other carbon atoms. Again, increasing stability as we go across, all right? And again, the reason why that is these hydrogens can't help stabilize this free radical carbon here. Meanwhile, this carbon can. As you add more carbon atoms surrounding it, the more it can help stabilize that lone electron in that orbital, right? And we actually did have this from our mass spec section. We're going to have decreasing bond dissociation energy. Remember when we created our fragments, bond dissociation energy was the amount of energy it took to break the bond, okay? Bond dissociation energy, okay? And again, it's going to fit that, right? Is what's going to fit. We're going to have a methyl. So we're looking at this bond here, break this bond right there, right? That is 435 kilojoules per mole. When we go to second primary, it should be less, and it is. It is then 410 kilojoules per mole. Whoops. Secondary then is going to be lower yet. That's only going to be 397 kilojoules per mole. And finally, tertiary will cost the least amount of energy of all. And to break that carbon-hydrogen bond will only be 381 kilojoules per mole. All right, again, just like from our mass spec, right? We said that this was the most stable. Again, decreasing stability, increasing stability going the other way, all right? I'd say if you have any questions, ask, but instead if you have any questions, email me, all right? We make some more room here. And we're going to go over free radical resonance structures. Remember, resonance helps stabilize our chemical structures, right? Whenever there's resonance available, the structure is more stable. It's no different for a free radical. But obviously, to have resonance, we have to have a double bond, right? Or more than one double bond. So let's take a look here. Right? This here is the allylic position, correct? This would be vinylic, this is allylic position, okay? So we can draw a resonance structure for this thing, right? Again, using a half arrow for a lone electron, okay? Well, there's pi electrons here, right, in a double bond. And thus we end up with this. Just like that. Pretty straightforward, right? Put your brackets. Blah, blah, blah. Okay? And then you can go back the other way, right? Let's take a look at a little bit more complicated example. Let's take a look at the resonance in a benzylic radical, right? Again, let me erase this. Well, I guess I can do it down here. Let's see here. Am I going to draw all these? I think I'll draw all of them, right? And starting off here. So again, here's our free radical, okay? So again, I'm going to draw the resonance structures for this, right? There's going to be, I don't know, I guess 4. Let's see here, blah, blah, blah. 4 resonance contributors. Make sure I get this right. Make sure I did that correctly. So now my electron is there, okay? I'm going to draw another one. Going to end up with this. Oh, that's terrible. Let me redraw that. That's horrible. Make sure I get this right. Da-da-da-da. There, there, and there. Do I have that right? Let me make sure I got that right. Ba 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 ba. Okay, yep, there. Let's draw another one. There. And then one more. It would actually go back. I ran out of room. Figures. Oh, is that terrible? And I end up with that. Sorry about that. Ran out of room, like I figured I would. Anyhow, so you can see we have all these resonance contributors. And again, you have to put that in brackets. Okay, stuck that over there. Sorry about that. But again, the more resonance structures you have available, the greater the stability. Okay, so this benzylic radical would be very stable. Right, let's take a look at some actual numbers for stability, all right? We'll take a look at a tertiary Again, we have decreasing bond dissociation energy going this way. Okay? Remember, tertiary was pretty stable, supposedly, right? We're breaking that bond, and we said earlier that that was 381 kilojoules per mole. I told you an allylic free radical was more stable, so it should have a lower bond dissociation energy. So let's take a look at an allylic position. And it does indeed, actually. Right, so that's an allylic position. We're going to break that. The bond dissociation energy should be lower, and it is. Here it is 364 kilojoules per mole. And then let's take a look at a benzylic radical. It should be lower yet, which it is 356. Again, to make our free radical here, right? And this is only 356 kilojoules per mole. All right? So again, meaning it's more stable. Right, again, I'd say if you have any questions, but email me, okay? Or again, take a look at our book if you have it with you. So remember, allylic free radicals are resonance stabilized and more stable. Vinylic radicals are unstable, okay? Vinylic radicals are unstable. And let's see here, what do we have here? I should have put this on the other page. I'll just quick draw it on the board. That decreasing bond dissociation energy, the